Greetings, friends. We are here on week 7. This is our second class of the week, and as I said before, it's the final one because tomorrow will be celebration. No class tomorrow, okay? So what we have for this week is to just remember PLC 7, which I have posted and is ready to go. Hopefully is something that seems manageable. We will have that for Friday. It is on the thermodynamics, so you may want to wait on that. You may not, whatever you like. As we've been saying, homework 3 plus celebration 1 is for Thursday, and the usual, all the usual applications, all the usual mentalities around celebration 1. Same as a quiz. It will be open during the day, nominally about 2 hours. And the usual kinds of things. Don't work together, and try not to get outside help. Like, try really hard not to do that. And I think I mentioned this at the beginning of the class, which was if we have anything there where I'm seeing people, like evidence of people working together or getting outside help, there is no second chance. That's the end of it for you. All right. So I'm going to ask you to drop if I find out that that's going on. Other than that, you should be able to settle down, have a stable internet connection, and remember that your time for the entire celebration includes upload time. So taking pictures, doing all that stuff, making it into a PDF, all that good stuff. All right. And in the midst of all that, try not to forget to turn in homework 3. You got to submit that at some point too, also before midnight. So if you're crunched up with this, maybe submit the homework first if you're going to do the celebration at the later points during the day. But anyway, that's that. We're going to go ahead and move on to some more thermodynamics today. And after tomorrow, where you'll have the celebration, we'll pick up with lab, and that's going to be our first thermo lab, hopefully. So we'll see how that goes. Alrighty, so we left off last time talking about, we talked about the laws of thermodynamics. We've talked about some of the quantities that are going into this. We talked a little bit about the ideal gas, kind of as a backdrop. Not the only backdrop, but the main one in which we're going to do calculations will be the ideal gas. I do want to have you think about other systems and what happens when we add energy to other systems, not just an ideal gas. So don't think we're confined only to that as the backdrop for this. However, we will continue on. We started talking a little bit more in depth about the first law at the end of class yesterday, so let's pick that up today and continue going on with it. So if you remember the first law, conservation of energy, okay? And what we're talking about is not, as I've been saying, not the macroscopic energies, not mechanical energies or things of that nature that you would have addressed in 4A, but rather the internal energies. What's going on when you heat something? What's going on when you do work on something? All right, so our expression for this involves the internal energy change of the system, right, which is why it's important for us to choose a system. How the internal energy change is based on how much heat is added or subtracted and how much work is done on the system or done by the system, okay? So let's take a look at a quick example. So this is really just this is a situation in which the system choice matters, all right? So let's just do a quick example here where we're talking about a piston and a cylinder, and we have a mass sitting on top of the piston, okay? So we're going to do this. We're going to have a piston cylinder like this, in which Okay, I have a mass resting on top of the piston. Okay, now of course inside the cylinder here there is a gas, and all right, so that gas is pushing on the piston just like the mass is pushing on the piston the other way. So let's suppose that the mass of things is such that there's a frictional force involved here. All right, so let's suppose that the gas expands and it has to push not only the mass upwards, but it also has to overcome a frictional force between the sides of the cylinder, the walls of the cylinder, and the piston. Okay, so the gas expands, and we would say, how much work does the gas do? Okay, so our question is how much work is done by the gas? And we'll assume that the piston is going to ascend some distance h, right? So if you imagine this could be the initial picture, and our final picture would be something like this. I'll draw a very raised piston. Okay, like that. We still have the same amount of gas in here. Okay, like so. And this distance is h. Okay, so our initial and our final. So the question is how much work is done by the gas in this case? Now we'll assume that the we'll assume a few easy numbers just to make the math a little bit more simple. So let's assume that we'll assume that the mass is 50 grams, and the frictional force that has to be overcome by rubbing the piston on top of on the side of the cylinder walls. We'll assume that frictional force is something like 0.2 of a Newton. Okay, so we'll look at that. If h is 25 centimeters, then the question is how much work was done by the gas? All right, so how much work was done by the gas? Well, in this case, we're thinking of work, and that's a force exerted during a distance applied. So what's going on then is that we would calculate the push of the gas, right? As it pushes the piston up, it raises the mass. Okay, so in order to push the piston up, it had to exert a force, and it exerted a force through the distance h. So the work done by the gas, at least to raise the mass, is known to be the force here, which is the weight of the block, times the distance it raised, so that's h. We could say initially that the work done is mgh, right? But we also have to add on the idea that there was a frictional force on the sides of the piston such that the work done by the gas has to include that, right? So since the piston raised 25 centimeters, this 0.2 of a Newton also acted during that time, right? So it had to push and overcome that frictional force as well. So really it's plus F of friction times h. All right. If we wanted to calculate that, we could certainly do something like that. And we could say that this is mass being 0.05, h being 0.25. I'm going to use g as 10 just because it makes the numbers a little bit easier, right? I'd go 0.05 5, 10, and 0.25. And I'd be adding on to that 0.2 times 0.25. Or in other words, 0.5 plus 0.2, and then divided by 1/4, or multiplied by 1/4. All right. So 0.5 and 2 is 0.7, and divided by 4, that's going to be a quarter shy of 2, so it would be 0.175. Is that right? 0.175 joules. Okay. So this is work done by the gas. If we were to draw energy charts, now I'm going to pause this calculation. We're going to come right back to it. Okay. If we were to draw energy charts for this situation, let me just move this H so I can draw the energy bars underneath here. I'm going to use energy bar charts to keep track of the energies, all right, which is something you may or may not be familiar with, but ultimately, as we use these things, you'll hopefully tune in. It's just the idea of energy is conserved, and so we do a bookkeeping in order to account for where is the energy and how much is over here and how much is over there and what type is it. So all I really do is visualize that with a set of bars, right? So you say I've got a bar worth of this much and it changed by that much. And so I'll show you right now what I mean. With this situation here, perhaps the energy of the gas was large because it was it's compressed. You know, maybe we've locked the cylinder down here and heated it a bunch up, and then we're going to unlock it and let the gas expand up or something like that. So this right here, I once again have the advantage of having squares on my whiteboard here. So I'm going to make a bar which is 5 squares. I'm going to say that's the internal energy of the gas initially. This is E internal, and it's I'm going to put a little I down here to show you that's the initial case. All right. Now the gas does work. Okay, so we can represent that in a couple of different ways. I could say, well, the gas is going to be doing work, and I could say that's going to take away from the internal energy, or I could say this internal energy here was divvied up into a bunch of other things. So that's what I'm going to do. I'm going to say that this became, some of it was still internal energy of the gas, but there's less of it because you'll notice the mass is now at a higher potential energy, right? A gravitational potential energy because we raised the mass. So the internal energy of the gas might now be only this much. E internal, this is the final state. Down here, I'll put that. Actually, maybe I'll put it up here, so we have that there. This is the final state. We will have, as I said, the potential energy of the raised mass. Okay, so assuming that we just started at 0 here and we raised it by h, so now it's up by some distance h, so we've got that. And lastly, since I have to conserve energy, this turned into thermal energy here due to the friction between the walls of the cylinder and the piston. Okay. So the energy that the gas begins with is divided up into things like this. So I have 5 squares here to start with, 5 squares here to end with. That's how I show energy is conserved. Okay, and that's how you should show it too, by making the bars have to add up. Okay, so either you could say I started with 5. I subtracted 1 because of the rubbing between the cylinder walls and the piston. I subtracted 2 because of this going up. So that was the work that left, right? And now I've got this left over, right? That would work as well. This right here is classified as the work done by the gas. This is the work that we just calculated right there, okay? But notice that it came from the internal energy of the gas, which means the internal energy of the gas is now lower. So the work done, now I got to go back to this calculation now. The work done is therefore, in fact, negative, because what happened was the energy of the gas dropped, so the work left. And that's what that negative sign means. It means from the perspective of the system, which is our gas here, that energy is no longer part of the system and it has gone, right? I'm lower in energy because of that energy leaving. So that's a negative work done by the gas because it lowered the gas's internal energy. Okay, so now, if you like, we could ask a system question, all right? Which is, we could ask, instead of asking the question how much work was done by the gas, we could say, what if the system was the gas plus the cylinder plus the piston? Okay, and we'd say, what is the internal energy change of that system? Okay, so instead of just having the system be the gas, which is implicit here, now I'm going to say my system is actually gas plus piston, excluding the mass. The mass is not part of the piston, and the walls of the cylinder. Okay, now notice that in that case, the work done by that system is different. The work done by that system does not include this as something that has left, right? This thermal energy, due to the friction between the walls of the cylinder and the piston, that's still part of the piston and the cylinder system. So if I change my system to becoming gas plus cylinder plus piston, like this, now how much work is done? Then this thermal energy does not classify as energy that has left the system because it has gone to heating up the piston and the cylinder walls. That's still within the piston and the cylinder. So the gas has expanded and done some work, but some of that work has not left, okay? That means the work done by the system now is only the gravitational potential energy increase of the mass, which would be only this first term right here, right? Which, as you can see, probably would be half of 0.25. And so that would be 0.125. Okay, right? It would be only this part right here. So choosing your system is important. Making it so that you have energy within the system, you have energy that's leaving the system, you have to think about what energy is still contained within the system and what energy has now left the system. Okay, so in these two cases, we'll get different answers. Neither one is incorrect. Okay, it's just an idea that you want to make your divvying up of the energy. You want to make the way that the energy divides up. You want to make it copacetic and consistent with how you've chosen the system. Okay, so if you chose only the gas, then you would have done this. If you had chosen the gas plus the cylinder and the piston, you would have done this, And then you would have said this little bar right here is still part of the internal energy of that system, because that's now all of the internal energy of the gas plus the system gas plus piston plus cylinder system. Okay. All right. Okay. So let's take a look at some more specific situations here where we have the ability to draw pressure as a function of the volume. All right. I'm going to say that in terms of drawings, these are two drawings that we're going to use fairly widely in terms of trying to visualize what is going on in these situations. It's really helpful to use the cylinder and the piston and just draw it out and see what's going on, and then to look at the energy bars. Okay, so these two are both diagrams that we're going to be utilizing in this section, as well as the one I'm about to show you here, in which we have the ability to plot the pressure as a function of the volume. Okay, and this is known as the PV diagram. So getting all of these diagrams to work together for you so it reinforces your conceptual understanding is going to be a real help for you in doing these. So we'll do the PV diagrams. And the first one we'll look at is a situation in which the pressure stays constant while the volume of the piston expands. All right, so in other words, if I start off looking at something like this, where I have the piston like this, whoops, okay, and the gas is like that, what we're going to do is we're going to go and say that the pressure of the gas here, I'm just going to call it pressure 1. Okay, like this. There's the piston. Here's the gas, the same amount of gas. So I got to count up all my little dots here and put a couple more in. All right, P1, still at P1. All right, same pressure. I want to ask this question so that you can get an idea of how we achieve something like this. Okay, so if I say that the pressure has stayed the same while the volume has increased, if I plot that, it's going to look like just a constant pressure, right? It's going to look like a constant pressure from V1 to V2, like this, going like that as it expands. So if I ask this question, let's choose the gas as our system. Let's ignore friction between the piston and the cylinder walls, and let's think about how we achieve this. I'm going to have to make a modification to this diagram here, because if I think about the piston simply expanding like this, I would have said, why is the pressure the same? If the gas, which is, I have the same amount of gas, if the gas is taking up a larger volume, typically what that means is it has a lower pressure. So how is it that in this case the pressure has stayed the same while the volume has gotten bigger? As part of a preview, I'd like to think about what must our gas molecules be doing. Now, I know what you're saying, which is this is supposed to be classical thermodynamics, and we're not supposed to be talking about molecules, because when this field was invented, we didn't have the ability to talk about molecules and atoms. That didn't come about until after 1900, 1905, in fact. So classically, we're not supposed to talk about this, but we know that they're there, so it's a little bit different for us as we're going through this 150 years later, or say almost 200 years later, almost. If the pressure has stayed the same, what must the molecules be doing in order to, right? Suppose that we're looking at just the beginning stage and the ending stage, okay? If that's true, then this piston is in equilibrium in both stages, right? In other words, it's not getting pushed up anymore and it's not dropping. The gas has expanded and it's keeping the piston right up there. How is it doing that? Well, by collisions, right? The gas molecules are hitting the bottom side of the piston, and they're doing it in such a way as to create a force which is balancing the downwards pull of the weight of the piston, as well as the atmospheric pressure on the top of it. Okay, so in this case, how is that force coming about? Well, the force is due to the change in momentum of these molecules. Well, they don't have to go very far, do they? Right? This one here is going to hit and bounce off that way, and then this one's going to hit and bounce that way, and then this one's going to hit. And they're all randomly going about, right? They're all randomly moving about, and every now and again they hit the bottom of the piston and tattoo it, right? And cause a force. Bam! Right? But it's an impulse that they apply. But now think about that same exact situation here where we're trying to describe, well, okay, what's going on with the molecules that are hitting the bottom of the piston? How far do they have to travel in order to continually provide that same force as we did in the first case here? They have to provide the same force over here. Would you say it's fair that these have to be traveling faster than these in order to make that happen? So if that's the case, and I think I would agree with you if you had said that, and I'm sure you probably did, you maybe whispered it, and that's why I'm getting this. I'm getting this feeling here that you're whispering that to me. So, okay, let's suppose that theirs are traveling faster. How do we make the molecules travel faster? Which means, in other words, we've increased their kinetic energy, right? We've increased the overall kinetic energy of the gas. How do we do that? We put a flame underneath it, right? Heat. We apply heat. So there's going to be a heat input required in order to keep this pressure constant. Now, again, think about the ramifications of this. If you look at it from the energy situation, this piston has a particular energy here. It's got a higher gravitational potential energy here. In addition to which, there was a pressure from the atmosphere here, which we had to push. So the internal energy here should be lower, but it's not. It can't be, right? Because ultimately, if it was lower, this thing would start sinking back down. It has to be such that these are moving fast enough to keep the piston at equilibrium. So their kinetic energies are higher here. In fact, they have a higher internal energy here than they do here. And that means we must have put in a lot of heat in order to make this happen. All right. When we look at the PV diagram here, which goes between the two volumes, this would be volume 1 and this would be volume 2. Right, to correspond with these two volumes in the cylinder. We talked about the way to calculate the work last time, and we came up with the idea that for a fluid, the work that we can calculate would be the negative of the pressure times, or negative integral of PdV. Okay, in other words, I'm going to take the pressure and I'm going to sum up the pressure times a little chunk of dV, and then I'm going to add them all up. So if I do that in this case, really what this translates to is the area underneath the pressure volume curve. And that means, in this case, it's the area of this rectangle. That area of that rectangle is the pressure times delta V, and that's going to be equal to the work, but we need to make it negative because that work left the system, and our system is gas only, right? It pushed the piston up, increased the energy of the piston. So that's going to equal, the negative of that is going to equal the work done by the gas. Hold on, I'm writing off the end of the board here. Okay, that's work done by the gas. Okay. This pressure, this situation in which pressure is constant is known as the isobaric process. All right. Okay. Let's take a look at it from an energy bar chart situation. I'm going to do a slightly different way of thinking about the energy bars this time. Here, there's an initial amount of energy in the system, in our gas, okay, like this. Okay, here's my initial state. I always like to denote initial and final in my energy bars. Okay, while this is happening, okay, I'm going to separate things out a little bit such that I can keep track of the heat and the work that have been put into or taken out of the gas. So I'm going to draw a circle here, and I'm going to say, pretend that that circle is my system boundary, right? This is just a representation. Pretend that circle is my system boundary. I want to think about what's coming in and what's going out from my system. In this case, we know for sure energy is leaving via the work because this got pushed up, and that meant that the energy of the gas would be decreased by the work done as it left, right? So 1, 2.5, okay, like so. This is work done. Okay. We deduced, however, that in the final state, the energy of the gas must be greater than what it started with because these molecules are traveling faster in order to get the same push on the piston and not let the piston fall. Okay, so there are, and another way you can think about it, right? In this case, how many collisions per time would there be on the bottom of the piston, right? A lot, because all of these molecules are pretty close, but these molecules are not all close, and that means there's fewer collisions in the same amount of time, which means that those collisions have to be harder. They have to punch harder. So the energies of these things have to be, the momenta has to be greater, which means the energy has to be larger. So ultimately, we're deducing that the energy in the final state has to look like this, which is a lot larger than the initial. Okay, that's the final state there. There's only one way to make this work out from an energy standpoint, right? We have to conserve energy. This is a law. There's no wiggle room here. We have to obey the law. So I started with some and I lost, but I'm ending up with more. So the only recourse I have here is to assume that I must have put more in. I put more in than I lost. I had to have. Okay? Had to have. So that's the heat that I've added. Okay. And now when I think about taking a situation like this, how do I show conservation of energy? Well, I take my initial I add to it whatever the change was, and that should equal my final energy. All right, so the change in the internal energy is really this minus this, and that should be equal to the net result of what happened here, which is some came in, some went out. I had to have a net of plus 2 boxes, so there we go, 1, 2, and there it is. Okay, so a lot of this is deduction. Okay, a lot of the great the thing that I really love about thermodynamics is the deductive possibilities that we get. Okay, so thinking about what's going on, even in just a simple situation like this, where I can draw all of this stuff out and show, hey, this is what's going on in order to make this work out. Okay, that's powerful. So we're going to use all 3 of these diagrams together like this in order to make judgments and reason out the situation that's occurring in the system. Okay. All right, so let's do this. Let's do this. Suppose that we'll try an example here, just in terms of the reasoning of things. So let's suppose I have this. Suppose that I'm given a PV diagram in which I have an initial state here and a final state here. And I'm going to go from the initial state to the final state. Here's I and here's F. I'm going to go to from the initial state to the final state in a couple of different ways. All right, I'm going to first start by dropping down here and then moving over here, like so. We'll call that path number 1. Okay, if you can see that, path number 1. All right, we'll call path number 2 the same as that, but going along the top and then dropping down into the final state from this side here. So we'll go this way, like so, and then down here. That will be path number 2, right? Like this. And then let's just assume that path number 3 is the hypotenuse straight across from one to the other. And that means like this. Call that path number 3. Like so. Alrighty. Let's start by doing a little ranking. So let's rank along paths 1, 2, and 3. Let's rank the work done along paths 1, 2, and 3. All right, so let's rank the work done along each path. Well, going back to here, we know that whenever I have something that's straight along at constant pressure, that's isobaric. That means the work done is essentially the area underneath the rectangle. Okay, so with that in mind, maybe why don't you pause for a second, see if you can come up with this ranking. Considering that these side legs, what's the work done in these situations? Would have to be 0 because there's no area underneath these. Okay, so if we rank by work done, then we're ranking from the curve or the line which denotes the pressure volume process all the way down to the V-axis. Okay, so for example, number 1 here, the work done by path 1 along this leg here and that leg here, well, this leg is 0 work. So the work comes from this one, which looks the same as that. So that would be a pressure times a delta V. Okay, that's a certain amount of area underneath here. Can you see that work done by number 2 is going to be much greater than that? And the work done by number 3, which is the area underneath, right, is going to be between those two. So in other words, if I ask, okay, let's rank by work done, 2 would be the greatest, 1 would be the least, and 3 is greater than 1 by a little triangle, right? 1 is a rectangle here, plus, if I go to number 3, plus that triangle. And if I go to number 2, it's the rectangle that's this big, all the way above them. All right, so we would go 2 being greater than 3 being greater than 1. And we would rank that by area underneath the curve, okay? So that would be the explanation. Now, what I'm interested in doing is, again, another ranking. I want to rank the heat transferred. Along each path, 1, 2, and 3. Okay, how much heat was transferred? Okay, now this is a buried question. In other words, it's buried in the first law. We need to use first law reasoning to do this because we can't calculate it. We don't know how much there is. We don't have any numbers. There's no way to calculate this. We have to come up with a way to figure this out. We have to rely on the laws. So if I know the first law, I know that the internal energy change is equal to the heat transferred plus the work done. Now, the key to this piece, though, is asking how would I rank, and this is intermediate to this, it's kind of buried in this, is the question, okay, how would I rank the internal energy change along each path, right? Because if I can rank the internal energy change, and we've already ranked the work, I can maybe rank what the heat transferred looks like, okay? So, and I should be careful here. I should be a little bit careful because 2 actually is greater in the negative sense. So really what I should have said here was rank the total amount of work done, rank the magnitude of the work done. I should have been careful with that, sorry. Here in this case, I'm going to say rank the heat transferred. So I'm going to rank the heat transferred by thinking about how much energy change there was in each path. Now, the initial state is up on the top left. The final state is down on the bottom right. Those states do not change. Therefore, the internal energy change is the same for everybody. Okay? Which means that if I think about the first law and I say, oh, okay, well, I need the work plus the heat to add up to the same number, right? So that means that I'm going to have to think about how much heat was transferred along path 2 versus path 1 and path 3. And if I had a large amount of work done in path 2 and not as much work done in path 1, but I need to add numbers to these in order to make them be the same, right? In other words, if I think about, where can I do this? I don't do this right up here. If I think about something like, if I think about delta E internal equaling Q plus W, right? Or if you like to think about it, because we're trying to rank the heats, so it could be something like Q equaling W, minus, could be delta E internal minus W, right? So the heat transferred along path 2, can you see, in order to make this, in order to make the internal energy change the same, right, I have to basically balance these two. So if I'm taking the internal energy change and I'm subtracting a large amount of work, or I'm subtracting a small amount of work, then it's different. So I have to be careful now thinking about, okay, if I'm doing this and I ranked the absolute magnitude of work, when I'm thinking about doing this, right, this is the other part of this kind of ranking. I should have been careful with how I did this. But when I'm thinking about looking at this, really path 2 had the most negative work, right? So when I think about the magnitude of the work, path 2 has the largest amount. Really, it should be the most negative work. So when I'm thinking about how much heat's transferred, right, in order to make the same internal energy change, where the work, the amount of work transferred was large, right, I have to have put in a large amount of heat. Okay, I would have had to have put in a large amount of heat. And the same kind of reasoning goes with path 1. Path 1, a small amount of work left. But in order to get the same internal energy change, I just had to replenish with a small amount of heat. Okay, so the heat ranking, if I rank the heat transfer, and I'm doing it the same way like this with absolute value bars, it should be the same, 2, 3, 1. Because I had to put in a large amount of heat in order to compensate for the large amount of work lost by path 2. I had to put in a small amount of heat to compensate for the small amount of work lost by path 1, and then path 3 was right in between. So questions like this are a little bit embedded, right? You have to, in order to get to this, I then have to start thinking about, well, what's happening with this, okay? And I didn't ask that explicitly, but that has to be something that you take care of. You have to tackle that along the path. Okay. All right, let's look at some other types of processes here. All right, so let's examine something that is like a leg here on the PV diagram. Suppose that I have a situation like this, where it's straight up or straight down, whichever you like. I'll call this initial to final going up. Okay, so if I'm thinking about this in a first law perspective, how much work was done, the answer would be 0 because the volume didn't change. Okay, now the pressure increased a lot. So if I go back to my cylinder and I go back to my energy bars, what is it that we're looking at here? I'm looking at a situation where I have a piston and a cylinder like this, and the volume is exactly the same. Okay? The volume is exactly the same, but I've increased the pressure. So this situation to that situation where I have an initial, say this is P of A, or I call it I. Let's call it P of I. P initial to P final. And I can't draw the greater pressure, but imagine there's a greater pressure here. So how am I dealing with a greater pressure? Well, I had to have put a lock somehow. I've locked the piston from moving. I've put something there so that I can increase the pressure and not have the volume change. All right, so once the volume is not changing, I know there's no work being done. And therefore, the question is, how do I raise the pressure so much? Well, exactly as I thought of last time, there has to be a large heat input here. Q has to be going in. I got a flame underneath it. Okay, from an energy bar standpoint, it looks like this. That's my internal energy of the gas. The gas is my system. That's the initial. Into my system, I am pouring a large amount of heat So I'm thinking of that plus that equaling this. Like so, maybe even one more. Like so. All right, so I've got the bar chart representing what the energy of the gas is doing. So that's at a higher internal energy than it was before. Has to be, because I just dumped a bunch of heat in and I didn't let it expand. Okay, the constant pressure was known as an isobaric. This is known as isovolumetric. Or if you like the newfangled name isochoric. I don't know where that comes from. Maybe it's a chore, like volume's a chore or something. It's a chore, isochore. I don't know where that comes from. So that's a process here in which the volume doesn't change, but the pressure increases. Let's think of another one. Okay, let's think of another one. This one's a little bit specific because now I'm trying to get into a little bit of ideal gas. Get into a little bit of ideal gas reasoning here. Okay, let's do this, initial to final, and we'll go that way. Okay, like so. Now this curve is a special curve. All right, so let's just explore a little bit about what this curve is. If I'm considering an ideal gas, this gives me a really nice way to implicitly think about what the temperature is. Okay, so the ideal gas equation of state, you may or may not know. And if you don't know it, then it's this. Pressure multiplying volume is equal to some amount of stuff times a constant times the temperature. Where this thing here, amount of stuff times constant, could be that, or it could be the total number multiplied by a different constant. Could be that. Those are interchangeable. Pressure, volume, and temperature are all the same though. Okay. Pressure, volume, and temperature are all the same. And make sure you're using the Kelvin temperature. Make sure you're using the Kelvin temperature here and not a centigrade or a Fahrenheit. That will steer you wrong. So make sure you're using a Kelvin temperature. How do we find the Kelvin temperature, you might ask? Well, that's a great question. The Kelvin temperature is the centigrade temperature plus 273. Because on the centigrade scale, minus 273 is where we found out that the kinetic energy of the thing goes to zero. Okay, so the gas would have zero kinetic energy at minus 273 Kelvin. Sorry, not Kelvin. Minus 273 centigrade. That would be 0 Kelvin. Make sure you're using that temperature in here when you are doing calculations with the ideal gas. Okay, the pressure and the volume, we can talk more about the units that we can use in those, but typically pascals and cubic meters are the way to go there. The situation of little n and capital R, or capital N and little k, those are just material. Those are material numbers. Right, so capital N here is the number of molecules that are in the sample of whatever it is you're talking about, and little n is how many moles of that is there. So that's like saying I have 35, or even better, say 36 eggs. Okay? That would be like capital N. Little n is like, well, I have 3 dozen. Right? So it's just a different way of counting the amount of stuff. Okay? And the constant here, capital R versus little k, is kind of just a thing that helps get the units right and tells us a little bit about the energies involved. All right. I don't want to use this numerically right now. I want to use it conceptually. So what I want to do is think about how is the pressure and the volume, how are the pressures and volumes related to one another? And what happens when I see a curve like this? And we have to be a little bit careful. Like, what kind of curve is this? Well, what if this is a situation where the pressure is proportional to 1 over the volume? Okay, so that's a reciprocal curve. Okay, if the pressure is proportional to 1 over the volume, that's like y is proportional to 1 over x. And it gives you one of these sliders, right, like that. But what that means is that it's not proportional to 1 over x. It's like I took the v and I slid it underneath here. That means the top of this is really all of this stuff times t, and that's not changing. Okay? So what this means is when you see these types of curves, and you have to be careful because there's going to be a couple that look kind of similar. This is a constant temperature curve. That means that anywhere on here, the temperature is the same. All right? Because if I'm dealing with the pressure being 1 over the volume, that means everything else is staying constant. And the pressure and the volume are balancing out based on what the temperature is. But that temperature is staying the same. Okay? So the take-home point here is that on every PV diagram, there's an embedded other graph that you don't see right away unless you're looking for it. And it's the one in which there's temperature curves. You can see the temperature on the PV graphs if you think about these lines that go like this. These are lines of constant temperature, and the temperature increases this way, out towards the 45 degree. This is increasing temperature, like so. Now, when I look at that process, does it make sense? If the temperature has increased, doesn't it make sense that the pressure is increased? And doesn't it make sense that the energy is increased? Because the temperature and the kinetic energy of the molecules are kind of related. Okay? So when I think about the PV diagram, I have to, in my mind, consider, okay, I've got a bunch of these other things in here which I can draw, which tell me a little bit about what the temperature is doing. Okay, and where are these points regarding different temperatures? Okay, so if I have something like this, where the pressure and the volume are related to constant temperature, if I draw the cylinder, what I have is a high pressure at a low volume going to a low pressure at a higher volume. So that means I'm starting like this. Okay, I have my system here. I'll put my system boundary here, and I know that I'm finishing with this situation. Maybe about the same number. I try to keep the same number. In all of these, I should probably say, but in all of these, the amount of material has been kept constant. Okay. So in this case, the pressure and the volume are reciprocals of one another. So as one increases, the other decreases because the temperature is staying constant. If the temperature stays constant, the energy is staying constant. That means that the internal energy here and the internal energy here is the same. In other words, delta E internal equals 0. Therefore, Q and W should be the same size. One's leaving and one's going in, right? So that means I've got, can you see? I've got work being done, but that means I must be adding the exact same amount of heat. Oh, whoops. I mixed my diagrams up here. Oh, sorry. I should not. I'm thinking about them. Yeah, that was good. Let's try it again. Okay. The internal energy. Okay, let's try this again. Man. All right. Q going in. Work going out, and that equals the final state. Okay. Whoops. That's good. How do I get from this to this? I have to have a flame here, right? And I'm putting heat into this, and as heat's going into the cylinder in the piston, the gas is then allowed to expand, and the piston rises, causing the pressure to drop, but the internal energy stays the same. Okay, in other words, they're still moving around at the same amount of kinetic energy, and therefore so it's almost like you think of whatever they intake from the heat, and then they suddenly start moving a lot faster, they give it up right away to the piston, which then rises, and then they're like, oh, back to the same thing. And then we absorb another piece of heat. Oh, we start moving faster, and then we push the piston, and now we're moving the same. All right, so that's happening kind of constantly. All right. Okay, good. So we've got a couple of processes under our belts. We're thinking about how are the PV diagrams related to the cylinders and the energy bars, and try not to mix those two like some other people do, and that's total craziness. What I want to do now is, we'll come back to some of this. What I want to do is talk a little bit about what happens when we have something I mentioned before. It's not an ideal gas. What if we have just a regular liquid? What if we have some water? Okay. I want to talk about what happens when we add heat to water, and we watch as we watch what happens. Let's put it that way. We watch what happens. Okay. Now, like I said, I want to concentrate on ideal gas systems, but I don't want to do it at the exclusion of everything else. So I want to think about what happens with let's do this. Let's start with a water system. Okay, and I'm going to think about adding heat. I'm going to add heat to the water. Okay, so I'm going to start with frozen. Okay, I'm going to start with ice. And then we're going to add heat. And then we'll eventually end up with boiling, hopefully. Okay, so imagine that this is a graph of temperature. And then along this axis, it doesn't really matter, but let's just say it's time. Okay, so that I'm thinking about ice. I'm starting off with a chunk of ice. And I have either put it in a pan and it's got a flame underneath it, or I'm letting it absorb heat somehow in an oven maybe. But I have the temperature, like let's say this, I have the rate of heat transfer being constant. Okay, so I'm putting in heat at a constant rate all the time. And what I'm finding is when I start with a piece of ice and I'm putting heat into it at a constant rate, well, the temperature increases. So what happens to the temperature of the ice is that it goes up like this. And I can write that that's the ice phase right there. But then what happens is something really interesting, which is that as I'm adding heat, I find that actually the temperature stops going up and it actually stays constant for a while. And I notice that the temperature stays constant for a while and then it starts to increase again. What's going on while the temperature is staying constant is in fact that the ice is melting. Okay. That's the melting ice stage right there. Now I'm adding, so now by the end of this, I've got all liquid water. I'm still adding heat at a constant rate, and I'm noticing the temperature goes up much slower this time. Much more slowly this time, takes a lot longer. Okay, this is the liquid stage. And eventually I get to another situation where the temperature plateaus again. And then all of a sudden I'm adding heat, but the temperature's not increasing. And so what's happening now, you might ask? This is where we are now boiling the water. We're boiling the liquid. And then after this, I come to a point where actually it starts to increase again, and now I have reached the third stage of different type of state of the material, which is steam. Now it's in the gas phase. Okay, so I got the solid, the liquid, and the gas phases, and I've got transitions between them. Okay, so we have a couple of things that we can talk about in terms of heat transferring here. When we have a situation where the temperature is changing when we are adding heat, that's normal, right? So we have these situations here and the one over there where heat is being added, or if you like, you could subtract the heat, you can remove the heat. And we notice a change in the temperature. All right, so this is heat added and temperature, and the result is that the temperature changes. What's a little bit strange, however, is that those two regimes are separated by situations in which I'm adding heat and there's no temperature change. Okay, that's kind of strange, right? Because typically you're adding heat and you're seeing, well, you're seeing the thing heat up, right? It heats up. That's what temperature increasing means. But now I'm looking at these 2 points here, or these two plateaus, melting ice and boiling liquid, and I'm saying, but the temperature's not changing. Okay, so what if we went back to the first law to try and find an explanation for this? It's a little bit convoluted, but examine it this way. We know that this number is not zero because we're constantly inputting heat at a rate which we've determined, whatever our oven is. Okay, so this number is definitely not zero. Okay, when you input heat and you see an increase in the internal energy, well, that corresponds to a temperature change typically, right? The internal energy changing means that, hey, yeah, you've got a increase in the kinetic energy of the substance, right? The molecules are moving a lot faster. Okay. Well, now let's think about what happens when we think about the work that's going to get done. Well, there's not a lot of work getting done here in these stages. That's just mostly it's heating it up, right? But let me ask, what would happen if the work was something in which that was taking some of the energy away, right? You're putting heat in, but you're not seeing a temperature increase. So maybe there's some work getting done, and it's kind of hard to see. But during these two phases here, what's happening is the bonds between the molecules are getting either here stretched or here broken completely apart, okay? And that is the work, right? That's a force exerted. That's like deforming and breaking a spring. You had to grab the spring and pull both sides of it. You did work on the thing. So in a sense, the Q and the delta E increasing here is what we're normally used to. Whereas there's a Q here and there's a W involved in these two, which are going to be indicative of the molecular bond stretching that's going on, or breaking, right? Because once you become a gas, there are no bonds between, or at least it's easy to model it as no bonds between the things. All right. Okay, so the terminology involved here is there's a modern component to it, and then there's a kind of old-fashioned component to it, and guess which one I prefer, but I'll tell you about both of them. When there's a heat added and there's temperature changes, these are indicative of what are called the specific heats. Okay, this is also what I would say is sensible, right? It's a sensible heat. You put heat in and the temperature went up. This is what you expect. Okay, so I would refer to this as a sensible heat. Okay, whereas in these cases here, I'm going to go around like that. In this case here, heat added, no temperature change. No delta T. This is hidden. It's hidden, and the word for hidden is latent. Okay, so we have sensible heat transfers and we have latent heat transfers. The sensible heat transfers are where we see the specific heat popping up, if you are aware of the idea of the specific heat, which we will get to in a little while. I guess next week. The sensible heat is where you see the specific heat popping up. The latent heat is where the latent heat pops up, okay? And the slopes are indicative of how much heat is required to change the temperature, and that's exactly what the specific heat is. The specific heat is how much heat do I need to change the temperature. So here I don't need very much heat to change the temperature because I'm putting in, remember, at a constant rate, and the temperature suddenly is rising quickly. Here the temperature is rising very slowly, which means I have a much larger specific heat here. So in these cases, the specific heat is like 1 over the slope, because as the slope goes this way, the slope gets lower, the value of the slope is less, but the specific heat is larger on graphs like this. So anyway, just being aware of stuff like that. And looking at that. So it seems like this is probably a good breaking time here. We'll pick up with this on Tuesday of next week, as we will have no class for the third part of the week this week. And I will go ahead and bid you happy celebration. I hope it goes well for you. Remember, please think about giving physics and not jumping into math land all the time. If you need to describe something, please use words and diagrams, okay, rather than math. I encourage that because that's where the physics is really done, and math is there as kind of a crutch. So it's there to kind of show stuff, but the real reasoning comes from trying to describe what's happening, all right? And that's done by words and it's done by pictures, and so please, in the celebration, think about giving me those, and especially when there's a conceptual question, and think about including them even when there's a math description that's going on. All right. So with that, I'll say happy times, good luck, stay strong, and I will see you in class next week. I'll see you on lab over the weekend. All right. Ciao for now, folks.